In the first section of graphical methods, I discussed the different types of graph shapes that you might see in honors physics. You learn their names and their general equation. What we're going to talk about in this video is how you write equations from the graphs that you have. So this is a general rundown of what you do when you get a graph. You have all these steps in your notes packet if you look at them, so I'm going to run through these relatively quickly. So once you get a graph, the first thing you always do is linearize it. Remember I mentioned before that the purpose of linearizing is to see if your hypothesis about the relationship that you're viewing in the graph is actually correct. If you graph the variables that are different from the standard y equals mx plus b equation, if your hypothesis was correct, then that's going to form a straight line. So first thing you do is linearize the graph. Second thing, you're going to write the general form of the equation using x and y. Third, you're going to substitute the actual variables for x and y. Fourth, you're going to find the values of the slope and y-intercept, which we will do these graphs electronically, so they will be given to you from the computer. You don't have to come up with them yourself. But then you're going to take those values and substitute them in for m and b. Always, 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 number 5, include units, and you must always simplify the units. Sometimes you'll have a unit that just looks all crazy to you, and as soon as you can simplify it down, it'll be a unit that you identify, and you can put meaning with it once you understand what the slope is, or y-intercept is actually trying to tell you. It's important to note that when you write an equation, anything that's a number gets units. So for us, that'll be the slope and the y-intercept. Anything that's a variable is not going to get a unit, so that's important to note. So when you look at the unit for slope, just like you find the numerical value for slope, you're going to take the unit on y over the unit on x. So the old rise over run thing is the same thing that we'll use here, except just for units. The unit for the y-intercept is simple. It's whatever unit you used on the y-axis. Once the graph has been linearized, you should be able to determine the relationship between the variables in the problem. So sometimes these problems will ask you to determine the relationship, so you should be able to give it as directly proportional, inversely proportional, no relationship, something like that, depending on the relationship that you're looking at. From there, you should be able to start to figure out the meaning of the slope and the y-intercept. And the only way that we know what the slope and the y-intercept mean is by looking at the units on each. And once you figure out what the units are, usually you can say, oh, if the unit is meter per second, then I know that the slope is going to be velocity, since meters per second is a unit of velocity. Or whatever the unit may be, you should be able to determine the meaning from what the unit is. For the y-intercept, we're also going to discuss a specific rule just for it, known as the 10% rule. The 10% rule is basically a statistical way to eliminate a y-intercept that you get in an experiment that shouldn't actually be there, meaning the y-intercept represents some error that you had in the experiment. So the way that we do that is we look at the biggest y value on your y-axis that you've recorded, take 10% of it, and if your y-intercept is less than 10% of your biggest y value, then you can eliminate it statistically. This gives you a more logical way to eliminate a y-intercept instead of just saying, oh, it's just error, and no matter what, just get rid of it. It's better to have some systematic way to evaluate your y-intercept. Here's an example of how I would write an equation from a graph that I'm given. So in this case, I've done an experiment of mass versus volume. This walks through the steps as we looked at them before, and I'm going to put the numbers on. It looks like the numbers didn't copy over from my PowerPoint. So there's the numbered list of the steps. So this is just following the example that I already gave you. So number 1 asks you to linearize the graph. Already done. Don't have to do that. Number 2, give the general equation. Well, in this case, it's a line, so it's y equals mx plus b. Number 3 is where you're going to substitute in the variables for the x and y. So in this case, on the y-axis, I have m, and on the x-axis, I have v for volume. Notice I don't put units with variables. Only numbers get units. So step number 4, I put the numbers in for the slope and the y-intercept. When you do these, you'll have the computer will tell you what the slope and the y-intercept are. In this case, the data box isn't on this graph, but I think you can see pretty quickly that we've got a slope of 1 and a y-intercept of 0. So I just put 1 and 0 in, and then I'm going to go ahead and write the units in. So I've got my y equals mx plus b becomes m equals 1 gram per milliliter times v plus 0 and G for grams. Now, honestly, if I were writing this, it's up to you if you want to leave that 0 in or not. If you left off that 0 grams, that's just fine. I left it there just for the sake of being able to talk about it. So in continuing that example, I can say I know what the relationship is between mass and volume because I can look at the shape of the graph. So when they ask you what the relationship is between variables, always look at the shape of the graph to answer that question. So in this case it's linear, so you can say mass is directly related to volume. If you said it the other way, volume is directly related to mass, that's just fine. Either way, it doesn't really matter. For the slope, you always look at the units of slope in order to determine its meaning. So in this case, if we look at the units of slope, the units of slopes are grams per milliliter. Our experience tells us that that's a unit for density. So that tells you that the slope, in this case, actually means density. For the y-intercept, there's two ways that we can talk about its meaning. The first thing is to use reasoning. So in this case, we can say, since we're talking about mass and volume, if we have something with no mass, what should its volume be? Well, if it has no mass, it should have no volume. So, or vice versa, you could say if it has no volume, it can't have any mass. So either way, you should be able to determine that the y-intercept logically should be 0. There's nothing that you can do to make a y-intercept in this case. So you can say that here it has no physical meaning. So if you were to find a y-intercept in your experiment, that's going to tell you have a little bit of error in your experiment. Now when I talk about error, by the way, I don't mean that you did something horribly wrong. Well, I guess you could have. But everybody, no matter how well and how perfectly you perform a lab, you're going to have a little bit of error in it. And, you know, it's never fair really to blame the experimenter. Really what you should be looking at is the limitations of your equipment. Especially in a high school class, we have our equipment is way more limited than what you'd find in a university or a research center or something like that. So when we talk about error, it's more just for the purpose of understanding that we have it, not to say that you're actually doing anything wrong. Now the second way that we can talk about the y-intercept is when I talked about the 10% rule. So the 10% rule says that if b, where b is the y-intercept, if the y-intercept is less than 10% of the biggest y value, then it can be eliminated. So in this case, the biggest y value was 10. So if you had anything less than, so if y max equals 10, then 10% of that would be 1. So if I have any y-intercept less than 1, that means I can statistically eliminate it through the 10% rule. So in this case it was 0, so that's pretty easy. But in general, it's 10% of whatever your biggest y value is. Anything less than that for your y-intercept, and you can eliminate it. So when I look at my general equation, all I'm doing is I'm taking what was y equals mx plus b, and I'm substituting in the variables that I've now determined it to be. So if my y equals mx plus b is now v was on my y-intercept, I said that my slope represents density, I said that my x value is mass, and I said that my y-intercept doesn't actually mean anything. That's why you can say v equals dm is then your general equation, which we commonly know as d equals mv for density, the equation for density. Here's an example that's a lot more challenging. I thought I would give this to you just to let you see something that's harder. The first one was a pretty simple example. So this is one that is about as tricky as they get, as tricky as at least we'll get. So in this case, I started off with kinetic energy versus velocity. My v there is for velocity, and you can tell that because it's in meters per second. So in this case, I start off with something that's a top opening parabola. So if I'm going to linearize that, anytime I have a top opening parabola, I'm going to square the x. So I look at my bottom graph and I see that I do indeed have a line. That means that my assumption was correct, that the data does accurately represent a top opening parabola. That's important because now I know how to write the equation for it. Okay, so the first thing that I'm going to do here, now that I have my linearized graph, is to work on writing the equation. So I substitute my variables in. So I've got kinetic energy equals m is just for slope at this point, times v squared. Now that little 2, that should be a superscript 2. I lose all my superscripts. Or I guess not those. That's interesting. Anyway, I lose my superscripts when I transfer this PowerPoint over into this program. So here you can see that the slope is going to be 5. Now check out the units. When you square the velocity, I have to also square the units for velocity. So velocity is meters squared over seconds squared. So that's how I end up with joules over meters squared over seconds squared, which is kind of big and ugly, and we'll have to see if we can simplify that a little bit. And you can see that the y-intercept in this case appears to just be 0, so that's handy. So here I can answer the question as far as what's the relationship. Because it actually is a top opening parabola, I can say the kinetic energy is proportional to the square of velocity. Now this part's a little bit tricky, and I chose intentionally one here that, like I said, was a little more complicated. But take a look at this. So if this is my slope, I'm trying to figure out the meaning of the slope. In order to do that, I need to simplify these units. So I get this big, ugly joules over meters squared over seconds squared. So what on earth am I going to do with that? Well, what you're going to have to do in this case is break down a joule. A joule is actually a combined unit, and we'll study that this year. A joule is a kilogram times a meter squared over a second squared. So that's what a joule actually is. So if I take that and I put that kilogram meter squared over second squared all over a meter squared over second squared, then I can actually cancel out my meter squared over second squared, and I get a kilogram. Kilogram, that's much happier. So since you have something with a unit of a kilogram, you can say that the slope represents mass. Now, in this one, it actually has one more complication beyond that, and you wouldn't be able to tell this unless you had actually done the lab. What you would find is, you'd say, well, what in my lab was constant that was a mass? Because I can see that the slope of this graph is constant, and it's in kilograms, so you should be able to identify something that you used in your lab that was constant. In this case, what you would find out is that the mass that you used, the slope, it will only actually be half of the mass that you used. So that's kind of a cool relationship, and you'll see that a couple times this year where there's something like a fraction involved that you wouldn't see unless you divide the two together, and you can find actually a factor between them. So in this case, there's actually a 1/2 in there as well. I told you this was a hard one. You wouldn't probably see that right away without a little bit of help, but that's okay. That's why we're doing it together here. And lastly, the y-intercept. So in this case, you can think again that if you have no velocity, so take whatever's on the x-axis and make it 0. So in this case, no velocity, should you have kinetic energy? No, because you know kinetic energy is the energy of motion. So you should be able to say that the y-intercept here has no physical meaning, and you can eliminate it. And in this case, again, I gave you a y-intercept of 0, but you could use the 10% rule if I gave you a non-zero y-intercept. So I can go back and make my general equation and say kinetic energy equals 1/2 mv squared. So the point with all of these graphs is to say that equations like this don't just come out of nowhere. When you do a lab and you look at the graph that comes with it, you should be able to find these kind of relationships from the data. You shouldn't have to look at a textbook. They shouldn't just appear on a formula sheet. You should be able to determine these equations on your own, because these are the equations that dictate the physical world that we live in. So it's not something that Newton or some other scientist just made up out of nowhere. Alright, and that is the end of writing equations from graphs. You should be able to complete worksheet 1. We'll try to do most of that in class. Whatever you don't finish then will be homework. But let's hope for the best, and hopefully you will finish it before then.